Welcome to my little crash course in OpenGL 3.2. Okay, as I said, this is a crash course. It's not going to have amazing detail or output or explanations. I'm just going to go through the basics of creating an OpenGL 3.2 application using SDL 1.3 as the windowing framework, etc. Yeah, as I say, the output's only going to be a red square, but if anyone likes this or actually watches it, I may create another tutorial afterwards which will go in further depth into certain things. I'm expecting that you know a bit of C++ and that you have a little bit of graphics experience, maybe even OpenGL before version 3. I'm going to code it all in Linux, and then we're going to see how we can use that same code in Windows with a little bit of an adaptation. Basically, I'll be coding in Ubuntu Linux. I think it's Jaunty Jackalope, I don't know what version, 64-bit, and my Windows is Vista 64. I'll be using Vim, the best editor in the world, and G++ is my compiler, and in Windows I'll be using Visual Studio 2008. So I hope this is useful to a lot of people and that it's enjoyable. I was tired when I recorded it, so it might be boring, but hopefully useful. So enjoy. So first we download SDL 1.3, which will allow us to create an OpenGL 3.2 context in a window. SDL 1.3 is still under construction, and so there's some warnings here about it being possibly unstable, though I haven't encountered anything serious, although there isn't really much documentation for all the new functionality. So let's create a temporary directory where we can work with this new source that we've downloaded. Extract it out here. Now we're going to want to build the SDL. So this documentation shows us from this configure, then make and make install. So we give that a shot, and we speed up the video a little bit. It'll take a bit longer on your computer, quite a lot longer. Okay, we got a problem with the make install. That's because it's trying to write to user local, which we don't have privileges to do. So we'll sudo make install. Hopefully you have administrative privileges. Otherwise you could actually just point your compilation to that build directory directly. There's some information about the installed libraries now and how to bind against them or link against them. So we're going to be using the third option. Bear that in mind when we create the make file later on. You may want to use the first option there in that list if you're creating many SDL applications. Okay, now we're just going to configure some of the test applications that come with SDL to see if the installation was correct. I mean successful. So build the binaries. We're going to use the testgl application. If this doesn't work, it either means that your SDL wasn't installed correctly or you haven't got OpenGL libraries or runtimes installed, but that's unlikely that it compiled successfully. Okay, so let's just install OpenGL libraries in case you don't have them. I'm going to use Aptitude as my package manager, which is what I always use. And we want the FreeGlut package, FreeGlut 3, and we want the developer libraries. Yeah. Hopefully now everything's built and installed successfully, and we can get on to the actual development of a OpenGL 3.2 application. Let's begin by creating our new source file. And we'll include the usual C headers, standard library, standard input output, as well as our SDL header file. This GLEXT prototypes define will basically tell the SDL OpenGL header file to declare and bind some of the functions we'll be using from the new OpenGL API. We'll quickly declare our basic main function skeleton and some prototypes for functions that we'll be using later on in the program. We'll now create the first initialization function, initialize context, which will initialize the SDL If any problems occur, this will return false, and the main function will return with an error code. The next step would be to create some flags for SDL so that the window will be supporting OpenGL and will be shown by default. Then we set up the frame buffer and its format so that we have 8 bits per color component. We set up the depth buffer, and we also enable a double buffer. The new SDL allows you to do multi-sampling in the frame buffer, so we tell it to have use 4 sampling. And those obviously set up which OpenGL version we'll be using, so which context to create. At the top now we're going to create some global variables to be used for the window, such as the width of the window, the height of the window, and some references to the window and its context. The global running we'll be using later on. So now we create the window with the title, its position centered, its width and height, and the flags that we defined above. If the window failed, then obviously we write out error message to the standard error stream and return false. Now that we have a window, we can create the context for that window. Once again, if this fails, we can return false. We're only going to be doing basic error checking in this video. The final command there just sets it to use vsync, vertical sync, with the monitor. At the end, we're going to want to release all the resources that we've created and allocated. So our release function first destroys the context and the window, and then lets SDL know that it can release all of its own resources at the end. We'll obviously need a makefile, so we'll invoke the G++ compiler in our case. It's just a simple makefile here because we're only going to have one source file for this example. The library parameters just let the compiler find the SDL libraries at the moment and find them at runtime, the shared libraries. So let's try and compile it, make it. Yay! Everything works. Great. No errors. Next we create the run function. Now the run function simply contains the animation loop. Our animation loop is going to check for events from the keyboard and mouse, and it's going to render or draw our red quad to the screen. And this will happen many times a second. Each iteration of this loop we're going to sleep for a set amount of time. The sleep allows other processes to use the CPU and also allows SDL's other threads to pick up events from the mouse and keyboard so that we can check for them later. We'll set the sleep time to about 10 milliseconds per frame or per loop. This allows us like a maximum of 100 frames a second. So our check events function is just going to basically ask SDL, has it received any events for the window from the keyboard or mouse, or other events. So we get an event using the SDL poll event. If it's a key down event, we get the key code. I'm doing a bit mask here because SDL 1.3 has done something strange with their key codes. I'm not really sure, but this seems to make it work. So basically, if the key was the escape key, set the is running to false, so that the animation loop will stop and our program can exit, as you saw earlier. Make it. We've got a problem. We haven't got a render function defined, so we'll quickly define one. There we go. Yay! Everything works. We can now move on to the OpenGL initialization stuff. So in our init OpenGL function, we first initialize shaders and then Vertex Array objects, which is basically our geometry in this case. Some render settings, and we set the size of our viewport for OpenGL, which will just take up our window pixel by pixel. First step will be to create shaders function. We'll need to initialize some handles for them, or declare some handles for them, or IDs. So there's the Vertex Shader. We're just going to be using a vertex and a fragment shader, very basic, that make up the program. We're going to declare the source statically, just like here, whereas normally you'd want to create shader source in their own files. to simplify the program, we don't have to have any file reading, etc. I thought we'd just do it statically for now, and I'll go over shaders in a future tutorial if people are keen. Simply put, the Vertex Shader takes vertex positions, moves them around according to the viewer's orientation. The Fragment Shader will then render any triangles onto the actual frame buffer, onto your screen. So it does the rasterization process, the coloring. So now we tell OpenGL we want to create some shaders, a Vertex Shader and a Fragment Shader, so it returns us some handles or IDs. Now the source code we've just used, we can assign to these shaders respectively. The gshprog will be the program that encapsulates the two shaders, links them together basically. So now we try to compile each of the shaders, and we want to check, like, did the compilation work? So we query OpenGL, we query the compile status of the Vertex Shader. If it failed, then we let the user know. Ideally we would return, this function would be returning false if it failed or something like that, just like our init context did, but it's not. Do the same thing for the Fragment Shader. It's always good to have error checking like this. And the get shader info log will print out the error message, so it'll tell us which line there is an error in our shader, for example. It's just like a compiler. The shader is compiled by your graphics driver, basically. Attach shader will attach each of those shaders to the shader program. And this delete shader will then flag them so that when the program is deleted, each of the shaders will also be deleted. Linking just links the fragment to the Vertex Shader within the program, and I would check if the linking was successful, just like we checked if the compilation of each shader was successful. And now we set this program, this shader program, as the one in use. As the last step of our initialization, we want to create our actual geometry. So we'll be using a Vertex Array object, as you have to do in the new versions of OpenGL. Our geometry is going to be a simple quad made up of a triangle strip, so 2 triangles and 4 vertices. The idea of a Vertex Array object is to encapsulate all the set of vertex buffers that will be needed. Now, vertex buffer, although it has vertex in it, doesn't need to store vertices only. It can store colors, it can store textures, texture coordinates, etc. Any attribute that a vertex may need. So you can have a whole bunch of vertex buffers, one for color, one for position, etc., that can be sent in to represent a vertex. And these can all be encapsulated by a Vertex Array object. That way you don't have to bind each of those vertex buffers each time you want to render. The Vertex Array object only needs to be bound, and it will remember it. So we generated our Vertex Array, we bound it, we're generating the own vertex buffer that we're going to use in this program. We bind it as the array buffer, and then we pass it our vertices in the quad array. We then set the vertex attribute pointer at location 0 to have 2 components that are floats, represent our vertex, and we enable it for the Vertex Array object so that it knows it must bind that vertex attribute 0 when we enable that VAO. And we create the handles at the top, and we made a mistake. There we go. So no errors. Now we just need to render the actual geometry. Our VAO is still bound, so we can just make the call to GL draw arrays. There we go, our red quad.